Moment. No. Okay. Gut. Mal schauen. Okay, das funktioniert. Okay. Also wir sind dabei. Okay, I speak English. Good morning, everybody. We are discussing applications of Gröbner basis. And the topic is now elimination. Elimination, it's a topic that was investigated quite intensely in the 19th century. So, okay, let me recall the definitions. I mean, first algebraically, and then I recall the geometric meaning of that. So I have a polynomial ID, let's call it J, over a field K in n variables, x1 up to xn. Okay, then I pick some L between and 1 and n. Last time I called it K, which was not very clever. And then I want to eliminate the first L variables. So the idea is eliminate x1 up to xl. So in the sense that I want to compute the Lth elimination ideal of J. And this is defined as follows. I denote the JL, and I just intersect J with the polynomial ring, which only consists of the variables xl plus 1 up to xn. So this means I pick out of J those polynomials that depends on the last n minus L variables. Okay, the one, if a polynomial in J contains one of the first L variables, I don't take it. Okay, and this is very easy to see. This is in fact an ideal in this smaller polynomial ring. So this is the elimination ideal. It's a bit abstract maybe, but then we already discussed last time the geometric meaning. So what was the geometric meaning? Okay, hold on, let me. So I want to see the chat down there in case there's a question. Right. Okay. Geometric meaning was the following. It gives the image under projections. So I look at the projection map going from k to the n to k to the n minus L. I forget the first L coordinates. I'm sure you are not, if I write a capital X, it's a variable, but here the small x is a field element. So this is the projection. Right. Then here I have the zero set of J. Okay, and this mapped to something. Maybe let's call the projection pi, or maybe pi L. Okay, I map it. Okay, so I get some set, but in general, the projection of, okay, which sets are nice in this context? These are the sets which are Zariski closed. So those are zero set of polynomials. Now, as it happens, if I take such a projection, it may be that the image is not closed anymore. So we had this very, maybe I just remind you of this very simple example of the hyperbola. Okay. So this is the zero set of x, y minus 1. Okay. If you project it down, what do you get? You get k without the zero. The zero is not there. Okay. So this is a simple example showing that this image, in general, you cannot expect it to be to be Zariski closed. But what you can take is the Zariski closure. I write it this way. Maybe I put Zar is the Zariski closure. Okay, I'm perfectly aware that I did not discuss all these details, all these concepts in details, but it's an illustration of what we're doing. And the theorem is now, actually we proved it, this is just the zero set of the elimination ideal. So this was, I think, let me see. We proved it. I have to look in my notes. Right, it was a, yes, it was a theorem. I called it a theorem that I proved. I hope you remember. So this shows that this abstract concept of elimination ideal has a very geometric meaning. Okay. Okay. Any questions on that?
Yes, there was one step in the proof which isn't clear to me, but I don't know if we have time now to.
Maybe can you ask at the end of the
Yes.
lecture? Maybe we can, then I will be happy to answer. No, yeah. Okay. Right. Okay. So the question is, of course, how can we compute such elimination ideals? And the answer is, right, if you have a Grabner gases with respect to a good term, appropriate term order, then it is very easy. So what are appropriate term orders? So these are the so-called elimination orders. So let's make some definition here. So definition. Okay, a term order on my polynomial ring. Okay, is of ELF. It's a bit funny. ELF elimination type. Actually, I don't like this word, but I think I took these notions from Cox-Lidloshy. But this ELF elimination type, okay. But what is the property? Okay. Take any monomial in the variables, okay? If this monomial contains one of the first k variables, then it should be larger than any polynomial in the last n minus L variables. So if, let me write it, if any monomial which contains one of the variables x1 up to xl is larger than every monomial in xl plus 1 up to xn. So the point is really, you should think of the first L variables. These are large in a way, in an abstract sense, in the sense of the term order. They are large, okay? So, example. Okay, example. So one, the lexicographic ordering, lex, with respect to this ordering. This is a elimination order, is of ELF elimination type for all L. Okay, let's do concretely. Let's say, okay, okay, let's make it concrete. N equals 3, I call the variables x, y, z. Okay, so for instance, you have, I don't know, okay, let's say L is 1. So if I have, I don't know, I have x, y to the 100, z to the 20, I just make up something. So this is larger than I don't know any. Okay, this is maybe a little bit stupid. Let's change it. Sorry. Okay, I put anything. No, this is larger than any monomial. Okay, over there. Okay, the reason is just that you have this x here. Okay, okay, this makes it larger. Okay, it's clear. Okay. So let's say there's a. Actually, when you work with this, then you will realize that the size of the Gröbner basis you compute depends on the chosen term order. So it's important to choose a good term order. So there are several options. Now we can, for instance, do the following. Let's assume I have any term order. Let this be any term order. Then I can modify a little bit so it becomes an elimination order. Okay, define for alpha and beta in n to the n. I say alpha less than or equal beta, and I put here the index L. Here is the definition. I first compare the degrees. So if I think of the alpha encoding a monomial, it has this degree. I compare with this degree. Okay, and if the degree of the alpha is less than degree of the beta thing, I'm fine. Okay, or they are equal. Okay, and then to break ties, then I use the given term order. So it's easy to check that this defines a term order. Okay, and then you see clearly see because of this here, I get an elimination order. Because if you have a monomial which doesn't depend on the last variables, then the sum of the betas will be 0. And you have another monomial where one of the first L variable occurs, then this is greater than 0. Okay, maybe I should have said it the other way around. Maybe I should have said, okay, sorry. If I have, let's say, alpha encodes a monomial which doesn't contain the first L variables, then this is 0. Okay, but the beta encodes a monomial where at least one of the first L variables occur, then this is at least 1. So it's okay. Okay. Right. Okay. So so maybe before proving the next theorem, a little lemma, which is useful. Okay, I assume I have a term order of Lth elimination type. Let the term order of Lth elimination type be given. Okay, and then I have a finite set of polynomials, non-zero polynomials as usual, finite. Okay, and I have the notion of the reduction mod G. This notion of reduction requires a term order, okay, because it relies on the notion of leading terms. So I have this, so I take a polynomial f, but it only depends on the last variables. Okay, and f reduces to h mod G. Okay, and then the point is, if this is the case, also h, the result of the reduction, only depends on the last variables. Okay, so by making such a reduction, no, okay, it's not possible that one of the first L variables sneaks in. This is impossible. And I can also say F reduces to H modulo the following set, GL, where GL is just G intersected, okay, with the polynomials depending on the last variables. Okay. Right. So in a way, it says notion of reduction is nicely compatible with this concept of elimination order. Okay. The proof is very simple. Let me write it. So assume F reduces to H mod G. So this means I find a term T of F, which is divisible by the leading monomial of some element of G. So there is also a G in capital G such that the leading term of G divides T. So this was the definition of a one-step reduction. Now you see, so where is it? H only depends on the last variables. So this term of F only depends on the last variable. And the leading term of G divides it. So the leading term of G also depends only on the last variables. So I can say the leading term of G, okay, I write it a bit in this funny way, but it's a polynomial in the last variables. This is the leading term. But then I can say also the polynomial G only depends on the last variables. And this is the property of the elimination order. So it follows that G is also here. You see, you have the leading term. This is the largest term of G. All other terms are smaller. Therefore, all the other terms also depend on those. Otherwise, it would violate the property of the term order being an L elimination order. So I have this. So then I'm done, I think. Hence, I see. In fact, I have a reduction of F to G mod GL. Okay. And clearly, I mean, what I do now, how do I get H? I subtract from F a multiple of H and right. You see from the definition, it's clear that H must be here in this polynomial ring. So in a way, this is in a way very simple. Okay. If it's not clear, you make one example and then we will be crystal clear. Okay. So, okay, but the nice theorem is here. So this shows how useful this is. So suppose I have a Gröbner basis of an ideal. Let G be a Gröbner basis of an ideal. Okay, I can call it I in the polynomial ring in n variables. With respect to, okay, a term order, respect to term order of Lth elimination type. Okay, then, okay, now, fantastic. I want to compute a Gröbner, actually, I'm given this ideal. I want to compute the elimination ideal, okay? Now this is very simple. If I have a Gröbner basis with respect to the elimination, this elimination order, I just pick out of the Gröbner basis those polynomials that only depend on the last variables. Okay. I only have to inspect, there is no computation involved. I only have to inspect these polynomials. Okay, and then the statement is this GL is a Gröbner basis of the elimination ideal. Of IL. With respect to, okay, actually induced term order, respect to induced term order. Okay, now here I'm very, very precise. I mean, I have my term order on the big polynomial ring. Now I go to this sub-polynomial ring, and of course I have just induced term order. So in particular, this GL generates the elimination ideal. Okay, if I would do this trick with any, let's say G would be any generating system of the ideal I, and I would do this, then in general this GL wouldn't generate the elimination ideal. Okay, but here it works. So okay, proof. So let's see. It's a nice and short proof where we can see the power of our concepts. So I think it's clear that GL is contained in IL. This is clear. Okay. Now, G is a Gröbner basis of I. This is our assumption. So then I know if I take any F in the ideal I, it reduces to 0 mod G. Okay. Okay, and now I apply the lemma. Now, right. Lemma gives. Now, if I pick F in the elimination ideal, okay, and I reduce, okay, then I know, okay, I reduce again to 0, but with respect to GL. So maybe I should go back to the lemma to illustrate again. Yeah, that's what I have. I mean, I have this, therefore I have this, okay, because the F only depends on the last variables. Okay, in particular, okay, okay, I can say for all F. Okay, now for all F in the ideal generated by, sorry, GL, I want to show that GL generates the elimination ideal, but let's go slowly. So I have this. Okay. Because GL is contained in IL. Okay, so therefore, GL is Gröbner basis of this. Because this was a theorem which characterizes Gröbner basis. Okay, if I have, maybe I should recall, if I have a collection of polynomials GL, okay, it generates an ideal. So what is a criterion